Imagine that we are distributed systems engineers. Our job is to provide a public API, a beautiful illusion to the world. And that API is, of course, firmly founded on tangible steel girders, the code that we wrote, which is beautifully structured and engineered to support the API, and that in turn relies on these wooden pilings, the language that we chose to write our high-performance system in. And that wooden piling, in turn, is driven into a firm foundation of distributed databases that we found lying around on the internet, represented here by this pile of tires. And as anybody who's ever worked with a database knows, the pile of tires is on fire. And this is our job as engineers to engage in what we call information hiding, to build the tower of abstraction higher and higher away from the flames, so that even while our engineers are screaming and throwing additional tires on the pile in a mad hope to stop the flames, customers believe everything is fine. My name is Kyle Kingsbury. You might know me as Afer, and my job is to set fire to databases and to talk to you about it. People, wonderfully enough, actually hire me to try out different distributed systems failure modes and to see what happens. To do that, I built a library called Jepsen. And this is a distributed systems testing framework written in the Clojure programming language that anybody can use to test their own single-node, distributed, concurrent system. Jepsen combines 4 main ideas. One of them is it is an opaque box testing system. We don't have access to instrumentation or simulation. We can't do code analysis. We're running real binaries on real Linux machines the way that God herself intended. And gosh darn it, that gives us power because we can test anything, including services that I don't have access to the source code for, or opaque binaries from beyond the moon. We do fault injection as well because real systems are characterized by recurrent partial failure. And that failure tends to be when all the interesting, fun stuff happens in the system. Distributed systems are fundamentally concurrent systems because things happen in different nodes at the same time. And when things crash, they become logically concurrent. And so we have to build the system to test concurrency from the ground up. That means that all of the data structures, all of the analysis is written with concurrency in mind. Fourth, it uses generative testing techniques. So we produce randomized inputs, we apply them to the system, and then we validate that some property holds. And the way this looks is that an operator sits at a control node, like their laptop, and runs a JVM program which uses the Jepsen library. And that program, the test harness, opens up SSH connections to all of the machines, the DB nodes, which will run the database being tested. And when I say database, I mean queue, cache, any sort of system that we want to test. They use the SSH connections to run some shell commands because this is DevOps, and we install copies of the servers and we let them talk to each other and form a cluster. And then we launch a bunch of clients in the test and have them talk to the different nodes and make requests and get responses. And that should look like a beautiful, coherent system, the rainbow that we're trying to build. And while that's going on, we start fires. We use the SSH connections to log into the machines again, and use IP tables to cut the network in half, and use TC to induce latency and kill processes and mess with the disks and so on. Now, how do we decide what to do? Well, there's a sort of a lazy generator, like a sequence of operations you'd like to perform. And this generator is written in abstract terms. It says, I'd like to read X. What is that? I don't know. It's just some variable. You get to make up the semantics of what your system does. Does it do reads and writes? Is it NQs and DQs? You make these things up. So let's read X, then let's kill node DB1, and then we'll set Y to 3. Those are abstract operations. And phrasing it this way means I can use the same generator to test different systems that have different ways of expressing, say, key value operations. So I take the first thing off the generator. I call it an invocation. This is an operation I want to perform. And I put that into the history, which is an append-only log. I then take that operation and I hand it to a client and say, hey, client 3, try to read X. The client says, OK, boss, I gotcha. I'm going to select star from from foo where ID is equal X, and I'll do some parsing, some network I/O, and what comes back is a completion operation that says, great, the value of X was 5. I put that in the log too, and I associate it with the invocation, so I know what the span of time was for that operation, how it completed. And operations in general can complete in one of 3 ways in any distributed system. They can complete OK, they happened. They can fail, and we know they did not happen. Or they could do something else, like a timeout. And when that happens, we log an informational message into the history, and logically, the invocation remains going for all time. It may have happened, it may never happen, it might happen next Tuesday. You just don't know, and this is the way that distributed systems work. So all the clients and the nemesis, which injects faults, are pulling things from the history, applying them to the system, putting operations into the history, and we build up this abstract history structure that has, reads and writes of X and Y, and then we can ask questions of that history, like, is it repeatable read? Well, to do that, there's a lot that goes into repeatable read, but a simple example is if I had a history that had a write of x5, which failed, and somebody else read x equals 5, and it succeeded, then I know I have an instance of G1A, aborted read. A failed transaction was visible to someone else. It's not supposed to happen at read committed or repeatable read. I've found a bug. Now I've proven the system is unsafe. So I want to talk to you about the last year's worth of research in 3 different systems, starting off with Buffstream 010. Buffstream is a Kafka-compatible log service. It's built for cloud deployments, and it does a bunch of cool stuff around data provenance and schema validation. But for our purposes, it looks like a Kafka. It actually speaks the wire protocol, and so you can take any Kafka agent, any Kafka client, connect it to their stateless agent, and that stateless agent will use a coordination service like etcd to decide which parts of the log belong to whom. And then it will store records from the log in some sort of object store like S3. And together, this looks just like it was a Kafka. If you're not familiar with Kafka, imagine I were a suburban housewife with a long list of vexations against my neighbors. And because I have so many grievances against them, I create a topic called grievances in my Buffstream cluster. And there's lots of them, so I actually partition into several different partitions, each one of which is a totally ordered log of grievances. And so partition 0 has offset 0, 1, 2, 3. Each one of them is some single message, some grievance I've added to the log. Now, there are transactions over these partitions, and at the read committed isolation level, they allow some interesting behaviors. And this happens in Buffstream, in Red Panda, in Kafka. This is how all of these systems work. They allow you to have 2 transactions, one of which sends X and Y, and some other transaction sneaks into the middle and puts Z in there. This would be analogous to like G0 if this happened in a traditional database. We call it a write cycle. Is it legal in Kafka? Well, depends on which part of the documentation you look at. Some parts say it's illegal. Some parts say it's fine. So, another cool thing that Buffstream and Kafka and so on do is that transactions that read committed allow you to write something. Another transaction can add a value after you in the log, and then you can read that value that happened after your transaction. This is circular information flow, also known as G1C. And it's a violation of read committed in a traditional database, but in Kafka, sort of unclear. It's not really discussed. In general, working with Kafka transactions is a little tricky. You sort of get a giant collection of switches and ways you can call code and how you reset offsets and how you do auto-commit and truncation. And depending on which combinations of parameters you use, you get various interesting effects. It's a bit of a choose-your-own-adventure book if you read those as a kid. So what do we find? Stuck consumers. You could have a partition containing A, B, C, D, E, and you poll it and get ABC, and you poll it and get nothing, and poll and get nothing, and poll and get nothing, and this goes on for hours on end. Just never going to get those D and E. Why? Well, when an agent restarts, sometimes it would return stale cached values for the last stable offset and the high watermark in the log. That was fixed in 013 RC6. Or you could have an agent which thought it held a lease in etcd, and etcd was supposed to inform it when the lease expired. But for sort of unclear reasons, the lease expiry event never made its way up into the code. And so etcd was like, you don't own that lease, someone else does. But the agent was like, I'm still in charge, I know what's going on. I think all of us can relate to this at some time in our lives, suddenly discovering that we didn't, in fact, have accurate information. This was fixed by polling etcd in 013 RC8. Sometimes you'd send a message like X to the log, and it would say, great, I've got that, it's at offset 0. And you'd say, okay, cool, what's at offset 0? And it's to have something completely different because your message actually went to offset 9,000. This happened regularly with crashes, partitions, pauses. It actually had to do with an error that happened inside of Buffstream, where Buffstream would have an indefinite error, and it would send an error message back to the client, like, hey, error code 123, your write failed. And you would think that the client would interpret an error code that's non-zero as an error and maybe throw an exception. And you would be right some of the time. Some, but not all clients, including the official Java client, would only know it's an error if the offset was also set to -1. For the error condition, they left it set at 0. And as a result, it was interpreted as a successful response. This was also fixed in 013 RC6. In 012, we found frequent write loss in healthy clusters. It would just throw a whole bunch of transactions on the floor all the time. This was ironically caused by a new transaction safety mechanism that was supposed to prevent concurrent producers from stepping on each other's toes during transactions. It was fixed in 013 RC2. The most interesting bug, and this is my favorite thing I've ever found in Kafka, or a Kafka-style system, is an aborted read case where some transaction would do a bunch of stuff, like sending 424, sending 926, yada yada, and then it aborts. And at a read committed, none of those things should be visible. But somehow other transactions managed to pull 424. And even stranger, although 424 was visible, which is bad, 926 and 927, written by the same transaction, never showed up, which is good. Huh. So we stared at this for a while, and I tore my hair out trying to jump between like 15 different Wireshark traces, and eventually we figured it out. Before this transaction, T0, this transaction earlier, sent a message to some partition, and it got back OK, and it tried to commit the transaction, and the commit timed out. And the client said, well, I can fix that. I'm a mature distributed system. I'm going to retry the commit. So it sends a second commit message, and that one completes OK, and then it returns to the caller. This is transparent to the caller. You don't know what's happening. And then it begins transaction T1. It sends 424, gets OK, 926, OK, 927, OK, abort, OK. This is all by the book. Everything looks correct. Except that commit message was still in the network, and it pops out later and causes the transaction to commit with just 424 in it. And then it starts a new transaction implicitly for 926 and 927, which of course get thrown away at the abort. In effect, it tears the transaction in half. And this is because commit and abort messages don't say which transaction they complete. Like normally you'd have either a transaction identifier or a sequence number, or maybe like an implicit ordering, like a TCP connection that tells you which messages apply in what sequence. But the Kafka transaction protocol just implicitly assumes that messages are delivered in order, even though the Kafka protocol itself delivers messages to any node over any number of TCP connections at any time. So that assumption of ordering wasn't actually there. So this is a fundamental problem. It led to aborted read, lost update, or lost write. You could write something, it would commit, and then be discarded. And sometimes you get half, but not all of a transaction's effects. And this happens in Buffstream and Kafka, and I assume it also occurs in anything else that's compatible with the wire protocol, because this is a protocol-level problem. In short, the Kafka transaction protocol has been fundamentally broken for years and needs to be redesigned, at least a little bit, to track this. This is Kafka 17754. There's also KIP 890, I believe, which tracks the same problem, but KIP 890 looks like it's just about a liveness issue, like transactions hanging. It doesn't really communicate clearly that you can lose data and that none of the transactional guarantees in Kafka exist. There are some mitigations, but they can't really solve the problem. Ultimately, this is on the Kafka team to mitigate. And there's good news. This is coming. I think the upcoming 4.1 release is going to bring in these fixes. Second database, Amazon RDS for PostgreSQL version 17.4. Postgres needs no introduction. It's an SQL database we all know and love. Traditionally, it was a single node system. It has a bunch of replication schemes glued on top of it. And the one that we're interested in is Amazon's RDS, Relational Data Store, I think. It's an AWS service where you throw money at them and they give you back a managed Postgres cluster or a MySQL cluster or other databases. And they handle all the tough work of replication and failover and backups. And you just get this magical pair of DNS addresses, one of which takes Postgres writes and read transactions, and the other one takes read-only transactions for the secondaries. Cool. So the SQL isolation levels as implemented by Postgres normally, read uncommitted is actually the safer read committed. Read committed is read committed. Repeatable read is actually snapshot isolation, which allows anomalies repeatable read prohibits, and prohibits anomalies repeatable read allows. Serializable is serializable, specifically serializable snapshot isolation. But you can't get that because on secondaries, Amazon RDS will throw errors if you ask for serializable and say, that's not safe. You got to go use snapshot isolation instead. So let's try it. Let's do snapshot isolated transactions across primaries and secondaries. We're going to append unique integers to lists, and we're going to read those lists back. And those are the two things our transactions can do. So when I say ry, that means a read of y. It could read y and observe the list 786. And under the hood, that means I did a select statement in SQL for id equals y, and I got back like a comma-separated list of 786. I'm storing my values as strings. The IDs, I'm going to write them as x and y, but they're really numbers. When I want to change something, I'll say append x10. That means I'm appending the string comma 10 using SQL concat to the end of that string value where the ID is x. OK. So really simple schema. Here are 4 transactions from an actual RDS cluster. Transaction 1 appends x 9, and transaction 2 reads x and sees the value 4, 9, which means that it must have executed after T1's write of 9. There's a write-read dependency from T1 to T2. Transaction 3 appended 11 to y, and transaction 4, well, it appended 3 to y, but later it read y and saw 11, 3, which means that T3's append of 11 happened before T4's append of y. Sorry, T4's append of 3. Therefore, there's a write-write dependency from T3 to T4. This is fine. T4 reads x and sees just the list 4, which means it must have executed before transaction 1 added 9 to it, because it didn't see the add of 9. And transaction 2 read y and saw nil, no value, and transaction 3 appended something to y, so transaction 3 must have executed after transaction 2. Hang on a second, this is a cycle. Wait a minute. This is actually a specific kind of cycle which I'm going to call G non-adjacent. It's a cycle where no two read-write edges are next to each other. This sounds incredibly obscure, and if you're wondering why do I care, it's because this is the exact kind of cycle snapshot isolation prohibits. But this is done by a snapshot isolated system. So that's against the laws, you know, like as Serial Mom would say, you know, the rules of databases haven't changed. This is also an anomaly called long fork. It looks like there's sort of 2 diverging timelines where T1 and T2 happen in one universe and T3 and T4 happen in another universe, and they didn't see each other's effects. This is also prohibited under snapshot isolation. This happens constantly in healthy clusters in every version we tested. And it occurs because of a difference in the way that Postgres controls the transaction visibility on the primary versus the order it writes to the write-ahead log. So I'm just making this up. I haven't looked at the orders for real, but you can imagine that the proc array order, the in-memory order, goes transaction 3, transaction 4, transaction 1. That would be acyclic under this graph. And the write-ahead log order might be transaction 1, transaction 3, transaction 4, also acyclic. And the secondary just copies the write-ahead log entries and plays them forward. And occasionally it executes a read-only transaction like T2 in the middle of those writes. But by so doing, it introduces a new set of dependency edges into the graph that weren't present on the primary. So the primary didn't know to prevent this cycle. It only shows up when you start adding the queries to the secondary because the orders aren't the same. So, is this documented? Amazon replied to this work and said, yes, it is documented. There is a 2013 mailing list post on PGSQL hackers by Ants Asma, and you, as a diligent Postgres user, probably read that post, right? I jest. There's also a 2024 pgconf.eu talk, and you all went to that conference as well. In short, as far as I can tell, there's no documentation for this in Postgres or AWS, and there really should be, because AWS already knew about this bug and just hadn't talked about it yet. Months later, there's still no docs for it, at least that I can find. AWS says that this might affect other replicated Postgres systems, which sounds plausible because it's an issue with the order of transactions inside the primary. And there is a proposed fix. Again, Mr. Osma has been working on that, but it will take time to get merged. It's a complicated problem to solve. So we can look forward, hopefully, to snapshot isolation in the future. But for now, be careful of long fork. Last but not least, TigerBeetle, version 0.1611. TigerBeetle is an obscure database that nobody here has heard of. It's a distributed database for financial transactions, and only financial transactions, or things that have that shape. Its entire universe, instead of being arbitrary objects or rows with variable schemas, its whole universe is accounts that hold something, like euro or kilowatt hours, and transfers between those accounts. So if I transfer 17 units from account 1 to account 1 will have 17 debits, and account 2 gets 17 credits. This is like a double entry bookkeeping system that we all know and love from accounting, if you love accounting. You can think of the database as an ever-growing list or set of accounts and transfers, every one of which has a unique ID. They're essentially immutable except for some derived fields like the balance of an account or whether it's closed. And this is really nice for a few reasons I don't have time to talk about in this talk. But the important thing is that every account and transfer gets a unique, strictly increasing timestamp in order of execution. And that property will come in handy. Transactions are strong serializable. This is one of the strongest safety properties you can get in any database. There are no interactive transactions, so you don't get to begin a session and do arbitrary statements and then close it. Instead, you send a one-shot transaction, which is like a batch statement, and it has to be all of one type. This isn't a theoretical limitation, it's just the way the API is shaped, but right now it's all a bunch of transfers or all a bunch of reads of accounts. You can't do a read-write transaction that's mixed together. But there's no reason the state machine couldn't in the future. To accomplish this strong safety property, TigerBeetle builds on 3 really cool papers. One of them is view-stamped replication, a replication protocol from the 1980s, which it turns out is also a consensus system like Paxos or Raft. Second is flexible quorums, work from Heidi Howard on making Paxos and other quorum-based systems safe by allowing you to trade off bigger quorums during leader election for smaller quorums during commits. And as long as you prove that any 2 of those quorums have to intersect, you can actually have a quorum that is smaller than a majority, which can be really nice for performance and fault tolerance. Finally, there's protocol-aware recovery, which is wonderful, sort of inspiring work on the fact that a lot of consensus systems are actually unsafe in the presence of a single disk fault and maybe a network or pause failure. Protocol-aware recovery describes how to identify, correct, and heal these disk faults by using other nodes in the network. So, how do we test it? I run Jepsen, and I spam a whole bunch of these operations at TigerBeetle. I'm going to create some transfers, create some accounts, query my transfers, look up transfers. And then what? How do I tell if those are correct? Well, I can get those timestamps, and I know every operation that I did was associated with some timestamp. So let me take those timestamps and go back and look at that concurrent history I talked about. I know the real-time order of what every operation did, when it started, when it committed. So I know that 5 was running while timestamp 7 was running, but they both completed before timestamp 12. So I'm going to look at this concurrent structure, and I'm going to draw a dependency edge every time one transaction completes before another transaction begins. That's a real-time dependency. So transaction with timestamp 7 completed before transaction with timestamp 12 began. Therefore, there is an edge between those 2. I'm also going to draw the timestamp order, which is from 5 to 7 to 12 to 23, just ascending sequence. And if these 2 are consistent with each other, if they are acyclic, then I've shown that the timestamp order is strong serializable. I've shown nothing else about the safety, but I know that TigerBeetle can hand out timestamps, and those timestamps are always uniquely, monotonically ascending in real time across all processes. If I found a cycle in this graph, if, for example, it handed out timestamp 23 and that committed, and then it began a timestamp with 12, I would know that this graph was acyclic and that it was actually not strong serializable for timestamps. Okay, So I've solved one small part of the problem. But what about the correctness of that sequence of operations? Like, what does it mean to create transfers? Is that correct? To do that, build a state machine. And the state machine is a re-implementation of TigerBeetle's logic from their documentation alone. So I did sort of a clean room build in a few hundred lines of closure. And it replicates all of the error types and all of the data structures and indices you need to do a query. And it just builds this giant single-threaded in-memory object. And you get a step function that takes that state and like a create transfers operation and the reply to it. And if those things are valid, if the reply lines up with what create transfers should have returned, it returns a new state with some modifications. If it doesn't line up, like if the create transfers were impossible because they'd already been allocated, or if the replies weren't right because it should have failed when it succeeded, or vice versa, then we'll return an error state. Now, I can just step through the timestamp ordered history of operations, starting off with an empty database state. I'll apply the first operation, create transfers. I'll get a new state. Then I'll take the second operation, look up transfers, and apply that. And then I'll keep applying it until I get an error. Like, oh yeah, during this query accounts operation, I thought that account 5 had balance 7, but it actually returned 8. In the real world, something here doesn't line up. Cool. So I can validate that the real-time order of transactions is consistent with the timestamp order. And I can do that in, it's mostly linear, but technically it's n log n because there's some sorting in there. And then I can validate that the timestamp order transactions are correct with respect to the state machine semantics. And again, there's some sorting and some like tree data structures in there, so this is n log n, but the expensive part is linear, stepping through those operations in sequence. And this is a lot better than doing general case verification of serializability, which would be NP complete. So we get surprising, oh wait, shoot, some crashes. We did find a couple bugs in TigerBeetle, which makes sense because it's a bug itself. Bug 2435 involved invalid pointer dereferences. Some of the very first tests I ran, like I would connect to the database and the whole JVM would immediately segfault. And it was like, what? Does anybody use this thing? And the reason for this was that if you ever interrupted a thread or called client.close, which is what my test did as soon as it hit an error internally, it would segfault the JVM. And the reason is that inside of the JVM library is a little piece of Zig code with FFI, and that's not memory safe in the way that the JVM is. It specifically allocated this packet object when it created a client, and it initialized a bunch of fields, but it didn't set the batch next field. And as a result, when you went to close it, it would try to dereference this packet.batchNext, and it would get in C, this would be uninitialized memory. In Zig, because it's got some cool memory safety stuff, it's actually 0x and that causes a segmentation fault because it's not an address in RAM you can get. Okay, so that was a straightforward fix, 01612, no longer crashes, fantastic. Shoot, time's out. Weirdly enough, if you issue a request to TigerBeetle, like create some accounts, the client, if it gets like a definite failure, like it can't even open a TCP connection because the server's crashed, most network clients will tell you, oh yeah, you got a connection refused. That operation definitely didn't happen. Do you want to try again? It'd be safe. But TigerBeetle's client, by design, never times out anything. And as a result, everything can only time out. So you just sit there for hours on end, never completing, never doing anything with your program, or because you're an engineer who has other things to do with your life, you time out the code and restart. But now you've converted a definite failure, something which you know did not happen, into an indefinite failure, something which might have happened or might not have happened. You can't tell. So this is a philosophical question. You know, do you want your client to surface these errors as different classes of thing, or do you want to have a sort of simple world where you only think about success and every non-successful network request is sort of pushed into the infinite future? I think that this is something that I would like to see changed, and we've argued about it. And I think the TigerBeetle will eventually introduce the error typology to do definite and indefinite failures, but doing that requires fundamentally rethinking the way errors are represented, and that will take some time. So this is still unresolved. We also found that if you crashed or isolated a single node, latencies would jump, and by a lot. You go from like 1 to 10 milliseconds. TigerBeetle has fantastic performance numbers. It will go from like 10 milliseconds up to 100 seconds, and the latencies would just stay there. Sometimes they would go back down, but other times they'd just persist for hours if the fault did. And this is really unusual. If you've ever worked on a consensus system, they're typically insensitive to single-node faults. You might see a brief elevation in latency, and then it should recover. And if you know view-stamped replication, or Raft or Paxos, you'd be expecting some structure like this, where the primary broadcasts a message out to a bunch of backup nodes, and those backup nodes are going to acknowledge in parallel. And as a result, even if one backup node is down, the other backup nodes can still reply quickly. They're not waiting for it. And as soon as you have a majority of these nodes on board with your commit, you can go forward and you're done. This is why Raft and view-stamped replication by default don't care about node failures that much from a performance perspective. But there's a drawback. This involves a broadcast, which means you're doing a lot of network I/O on one site, and TigerBeetle has to do a lot of network I/O and wants to reduce that bandwidth impact on any single node. So they do ring replication. And as a result, if the next node in the ring is down, that message never makes it to anyone else. And instead, it goes through a recovery procedure, which is a good deal slower. This is fixed with two different changes. In 0.1643, the ring is now bidirectional, which gives you 2 chances to reach the rest of the cluster. Now you can handle multiple faults. And the ring is now this virtual topology that can adapt to changing conditions. So as TigerBeetle sees that nodes are crashed, it'll push them farther away in the ring, and it'll bring nearby nodes, like those that are in the same data center, close together. And that actually improves common latencies as well as failure latencies. So I think that's a big success. 2544 is the only real safety bug we found in TigerBeetle. And it involved a query which looked for a code and a ledger, or any 2 fields that were intersected. And this returned something like, hey, I got your transfer ID 5, it's got code 2, ledger 3, here's the debits and credits, blah, blah, blah. But what's missing is that there's all of these other transfers that should have been there, other transfers with code 2 and ledger 3, which didn't appear. It looked like TigerBeetle was just giving up partway through all the queries that had 2 or more predicates. And this is a cool bug which I can't even begin to explain in detail. They understand it far better than me. But the high-level overview is that when you do an intersection query, TigerBeetle will do what's called a zigzag merge join between 2 different sorted indices, and it will go back and forth between them, ascending through keys, finding everything that matches both. And in that process, if the keys were out of order in a particular way, it could push the bounds for the allowable keys so small that the current key it was looking at would fall outside the range, and it would say, oh, I'm done, I've looked at everything. That improper bounds contraction caused it to skip over records partway through. And this was missed by all 4 TigerBeetle fuzzers. I want to emphasize, TigerBeetle has probably the strongest testing culture of any database I've worked with. They have extensive simulation tests, really detailed safety checks at multiple levels of the system. And the only reason I got lucky here and found this bug is because it required A, an intersection query, which only some of the fuzzers did, and B, out of order values. You had to write like 152, not 125. And I happened to do both of those things in the same test, but the fuzzers did them separately, and so they never got this particular code path. That was fixed in 0.1617. No data loss here. It's just a query bug, so some records may have been missing in previous results for queries, but they will show up if you do them again at a higher version. We did new disk faults in the TigerBeetle test, and I'm really excited about this. One of them I've done before. We flip bits on disk to simulate like bit rot. A cosmic ray comes in and realigns some of the bits on disk. We just flip a few of those in the file, kill the machine, let it restart, and see what happens. And that actually found some panics, surprisingly enough. TigerBeetle also did really good simulation tests for bit faults, but if I recall right, they did them kind of like sector by sector and didn't introduce single bit panics in this very particular spot. It turns out that if you flip a bit in the unused section of the file, a padding section that doesn't contain anything important, that padding section is normally all zeros, and TigerBeetle for safety would assert that they were 0. If a bit flip happened there, it didn't affect safety anyway, but the assertion would say, oh, that's supposed to be a 0, not a 1, and explode. So this is just an overly zealous safety assertion. Like TigerBeetle's culture of safety was slightly too strong here. And that was fixed in 01626. We found a few panics in different regions. Other faults that we injected included copying regions of the disk file around. So you take TigerBeetle has a predictable disk layout, and we actually made the fault injector aware of that layout. So it takes like a region of the file that is supposed to be one record, and it copies it somewhere else. And the idea is that if TigerBeetle did like checksums next to the records themselves, you go copy the checksum in the record and put it somewhere on disk, and when you read it, you think, oh, everything matches, it's good. No, TigerBeetle's smart. It puts the checksums far away so they can't be misdirected in the same write. We also did snapshots and restores. Take a region of the file, squirrel it away on disk, let the file change, and then bring it back. The idea here, again, is to produce structures on disk that look valid so the program gets confused and does the wrong thing, rather than just complete hot garbage that would be easy to detect. And unfortunately, neither of those found faults. This is actually really vexing. We injected these faults on minority of nodes, so we would corrupt like the entire file on a disk, or delete it, or we'd corrupt some parts but not others. But we'd restrict these faults to a minority of nodes, because if every node fails, or if a majority of nodes start lying about the disks, like there's really nothing you can do. This is a minimum requirement. In most systems, TigerBeetle is better. TigerBeetle allows us to, some of the time, inject faults on every single node's disk, so long as those faults never land in the same region of the file. So what we call a helical fault involves node 1 bytes 0 through 100, on node 2 bytes 200 to 300, on node 3, 300 to 400, and so on around the disk, so that every single part of the file is corrupted, but somebody has a copy somewhere. Most databases would just lose their mind at this, but TigerBeetle is like, cool, I got you. Thanks to protocol-aware recovery, it detects these faults, repairs from other nodes, and it can do this in the superblock, in the replies section, and in the grid, which is where all the data is stored, the big part. It can't do this in the write-ahead log, which is just because the write-ahead log, the way it gets appended, it's possible that the important part is at 2 different places in the file, and so if you corrupt both of them, you can lose an invariant. But the fact that it can do this in most of the file is frankly shocking, and I'm really impressed. So having looked at this, I'm actually sort of embarrassed. Jepsen has a little database inside of it for the thing it writes to disk, and I write down this file with all the stuff that happens in the history, and I realized while I was writing TigerBeetle tests, all of the ways I was doing it wrong. So now I have to go back and rewrite it. As of 01643, TigerBeetle looks to be strong serializable, and this is one of the strongest verifications I've done in Jepsen because we do the whole state machine. It's not just list, append, and read. It's almost all of the operations except for timeouts and a few other corners of the API I couldn't figure out how to test. All of the issues we found are fixed except for number 206. That's the request timeout issue. Should be fixable, just a question of kind of thinking things through and designing the right shape up front. And also bug 2745, we found a minor crash involving upgrades that was relatively infrequent. And it was judged that rather than going back and redoing the release, it was better just to document it because it was several releases ago at that point. To wrap up, sometimes when you are looking through your database state, pulling out records of the REPL and investigating them, you'll say to your colleague, Ralph, I think we have bugs. You'll find records that have impossible pointers and people who are both deleted and created, and you'll start to think to yourself, maybe I made a mistake, and maybe you did, or maybe the database is wrong. What I found is that writing simple tests for databases can yield surprising results, and I want to encourage engineers in general to do these tests. In particular, I think it's valuable to have end-to-end tests as a part of the complete breakfast of testing. So you want formal methods and proofs, both by hand and machine. You want model checking. You want abstract execution, simulation testing, little unit tests, generative tests of your code, fuzzers, all that good stuff. But at some point, you want a test that actually runs the real binary with clients, with dependencies on operating systems and networks, because sometimes the problem is in the interaction between those components. as we saw with etcd in Buffstream, sometimes a failure in that component can cause what was otherwise correct code to do something wrong. Sometimes a client library interprets something differently than you thought, or has a crash. So do some end-to-end tests. Second, do fault injection, because systems do the interesting stuff when things fail. Use kill to kill processes, or pause them using sigstop and sigcontinue. You can induce latency with TC on Linux. You can use IP tables or NF tables to partition the network. You can set the clock and get systems that depend on clock safety to do really fun things. When you're doing these tests, it's best, I think, to generate random inputs to the system and then to validate that some property holds. First off, writing example-based tests like set x to 2, should x be 2, those become impossible as soon as you go to distributed systems because they're concurrent, and if the set of x of 2 times out, it could take place at any point. Now you don't have control over the order of execution anymore. So you need to start thinking about concurrent generative tests from the very start. And simple properties like, can I ever register the same username twice, are fairly straightforward to write tests for. More sophisticated problems like cycle detection between transactions can find more subtle bugs. All of the bugs that I report in this analysis came about from L, which is the safety checker I've been working on with Peter Alvaro at UC Santa Cruz. When we talk about safety, there's kind of three things that have to line up. There's the abstract formalism. We talked about those dependency graphs in snapshot isolation. That's an abstract relationship between mathematical concepts. What the documentation says might be something altogether different, like repeatable read or snapshot isolation. And then there's what people have in their head, which could be something altogether different. By aligning these three things, getting a good intuition for the formalism and having the documentation communicate that to users, I think we can build safer software. Software that prevents meaningful invariant violations, that doesn't light on fire in a way that people see. So I want to encourage users to read a little bit of the database literature. Atul Adya's 1999 thesis on weak transaction isolation is incredibly approachable. It's 25 years old, and it introduces you to exactly why the ANSI SQL specification is so bad about transaction safety, and it makes a magnificent effort to standardize these things in a sensible way that works for lots of different databases. Just the first 3 chapters will give you a great understanding. Second, read the documentation for your system, because sometimes the documentation is not clear, or it's buried somewhere in there that you have to do certain things to get safety. And sometimes the documentation's wrong, so check your application safety on the database yourself. If you have the time, and I know this is asking a lot, try to write some tests end to end. And if you find something unusual, I want you to share it. I would love to see people writing up, even if they got it wrong, even if you misread the documentation, it's useful information that you misunderstood it. Because that says that somewhere the documentation wasn't clear, wasn't surfaced in the right way, or you didn't have the right mental model, or the formalism was wrong. I think it's actually helpful to write up the successes and the failures there. For vendors, it's important to read the literature because, you want to build something that other people understand, and also read the reports to formalize the safety model, and then to communicate that through your documentation, and then test that safety model so that you actually know that the system does what it's supposed to. For academics, I think that looking at these user reports and these new systems that are coming out, like Kafka-style logs have transactions now, what is the safety model for those transactions? There's not a clear definition of what the anomalies might be or what the safety level should be, and knowing that would help us compare systems and maybe tell what kinds of transactions are safe in what contexts. And ultimately, this work is not helpful if it doesn't connect back to the vendors who build systems and the users who operate them. So in addition to all the wonderful proofs of abstract executions and history structures, I think a lot about the Raft paper, which was rejected several times for not being novel enough. It's sort of a, Raft, we have Paxos at home. Like we're not going to McDonald's. But because it wasn't new, consensus was a solved problem. But what the Raft paper does really well is it builds a system that's written for mere mortals like myself to understand, to read, to implement, and it sparked a renaissance in distributed databases. Lots of people implemented much safer systems because of that paper. So I would love to see more papers written with that kind of pedagogy in mind. All right. I have so many thanks to say. Buff Technologies Incorporated funded the Buffstream research. TigerBeetle paid for me to look at TigerBeetle. And the RDS Postgres report was done just pro bono in my free time. Peter Alvaro, my longtime friend and collaborator at UC Santa Cruz, helps out with almost all of these analyses. A big round of applause to Artem Lifshitz and Justine Olshan from the Kafka team, who helped to understand what was going on with transactions, and Ellen Marie Dash, who helped me write some very basic Fisher-Price C code to do the file system fault injection. Thanks to all of them. Thank you to you for coming to this talk. If you'd like to learn more about this research or to hire me to test a database, you can go to jepsen.io. All the tools, all the reports are free. Thank you very much.